Well, hi, everybody. Welcome back to day 4. We've spent an awful lot of time working on programming, but I figured it was probably time that we spend some time with graphing. Creating visualizations of data is a hugely important field, and a lot of research has gone into making really great tools for this. So today we're going to be working on this very important capability for data science. Hopefully everyone has downloaded the script for today from the directory. I am using a lot of examples that were produced for Columbia University at this URL. Feel free to look there. I have also borrowed a little bit from the set of people who've written about data visualization. I think that this post on towardsdatascience.com was really useful. I didn't include that URL in the script, but I wanted to read this little section because it's going to be hugely relevant to understanding how Ggplot does its thing. So I want to start by, I'll actually quote from the author of the tools first. Back in 2007, a manuscript was submitted on a grammar of graphics. Grammar of graphics is kind of an old idea. It's been around for some time, but people have been working on developing how we describe the way we get to a visualization starting at a data set for some time. So Hadley Wickham is the author on this paper. You can see his name figures very, very prominently in everything to do with Ggplot 2. He also shows up a lot in connection with another set of libraries called Tidyverse. Personally, I find Tidyverse kind of difficult to explain and to use, but we have some real experts at it at our university that I'm sure would be glad to talk to you about that if you'd like. But Hadley Wickham has done quite a lot to popularize visualization of data for the data sciences, and this paper in 2010 is kind of the one that set it all in motion. So when we say Ggplot, we're talking about the Grammar of Graphics Plotting Library version 2. And it's worth knowing, since many of you are starting your graduate careers, that the Grammar of Graphics exploded out of Hadley Wickham's thesis, right? So this is this library, this software tool that launched his career, and many new people have entered the field assuming that Ggplot 2 is the way to work. Have had their careers launched by what he was able to produce as well. So the layered grammar of graphics that he introduced about a decade ago has really just won over a huge number of people in the R community over time. So the grammar of graphics gives us a way to talk about our data and how it will be represented on screen in a structured way. So as we produce these plots, I want you to remember that in each case where we use Ggplot, we're going to create a Ggplot object to begin with that encapsulates our data. And from there, we're going to talk a little bit about aesthetics and a little bit about geometric representations of data. So aesthetic and geom are things that show up all over the place anytime Ggplot is in motion. So I'll just read this section out loud. Data, always start with it, these objects. Identify the dimensions you want to visualize. Just because it's in your table does not mean it has to end up in in your visualization. We often abstract away details that are less important. Aesthetics. Confirm the axes based on the data dimensions, the positions of various data points in the plot. Also check if any form of encoding is needed, including size, shape, color, and so on. Think about that. Now each symbol that appears in your image is going to have some position that's relevant to the data that underlie it. It's going to have some color. It may have a size, maybe a huge triangle or a small triangle that may represent it, and it's going to have some color. These are all axes that we can use to encode information in what people are seeing. Okay, scale. Do you need to scale potential values? We frequently see people using log scale for representations of large numbers, especially exponential curves. So is it appropriate to use that scale to transform the data that we're visualizing? Geometric objects. and this is where one of the big terms of Ggplot shows up, the geom. This is going to cover the way that the data maps to some feature in the visualization. Maybe it's going to be a scatter plot, in which case you've got points or little symbols throughout your plot. Maybe you're going to use bars or lines or whatever. Frequently, we make use of statistics derived from our data to report them. We're going to see an obvious example of that when we do box plots, because a box plot is not going to represent individual data points unless they're outliers. It's going to represent the range of the data. It's going to talk about the quartiles, the median of the data. Facets. Now, facets is kind of an odd one. It took me a while to get my head wrapped around it, but frequently we have different subdivisions in our data set, and each of them gets its own little subplot. In the world of Ggplot2, that's going to get called a facet. And coordinate system. We often think about our options for putting things on an X versus Y plane. You know, thank you, Pascal, and all that. But occasionally, it makes sense to make use of a polar representation of our data instead. So I just thought that this was a useful kind of checklist to be thinking about. Items 1 through 7 on here. The URL should be apparent from the top of the window there. Okay, so with that said, let us now do our acid test. You've now installed the Ggplot2 library. We want to ensure that it is actually something that you can load into memory to make all of its objects and functions accessible. So if you type library Ggplot2, you should get started. All right, now mine throws a warning, as we know, because my Ggplot was built for 3.4.4 and I'm running version 3.4.0. Again, not going to pose a big problem here. Is anyone unable to get past running library on Ggplot2? Everyone's able to get past that. That's good news. Good, okay. If you didn't have that installed, you're going to have it installed for almost all of the visualizations we do today. So that's a good place to start. Happily, some of the standard data sets that we can use to test these visualizations don't have to be loaded from a file or manually entered or simulated. Instead, we can just use some that already exist. So IRIS is a really ridiculously popular data set for the context of this visualization. So here I'm running the summary on IRIS. So you can see I didn't have to tell it where to find IRIS. I believe IRIS was introduced alongside the Ggplot2 data set here. So because I've told it I'm going to use the Ggplot2 library, IRIS is automatically available. It's already named for me. It's already here. So I can see that running summary on IRIS is going to show me a variety of fields. So we have sepals and petals. Both of those have length and width fields. And then we have species. All right, now somebody here is probably a plant scientist, at least in the making. We have a few plant people? In the making? Okay, a few people, good. Well, I think that all of you will probably be better placed to tell us what a sepal is. A sepal. Anyone for a sepal? I like that definition. The little green parts under the petals. That's okay. We'll deal with that. All right. So we have petals, the little bright-colored bits of the flowers, and we have leaves. They're the green bits on the sides of the shoots, etc. And sepals are kind of. I'm going to really just do brutality to plant technology here, but I'm going to say that the sepals are sort of specialized leaves that hold the flower. Is that atrocious? We'll call it good enough for now. So in this case, we have a researcher who has gone to examine 150 flowers. There were 50 of the Setosa species, 50 of the versicolor species, and 50 of the virginica species. And all of these are what kind of flower? Irises, that's the name of the data set. Very well done. Okay, so we have sepals, petals, and we have the species. Each of sepals and petals have lengths and widths. All right, that's the data set we're going to use. Now, I believe yesterday I made use of this function, but I included it in the script today, that we can take a look at the top of the file with head, and we can look at the bottom of the file with tail. So I just say head iris or tail iris And what we see is that this file has already got some sorting to it, right? We see that the Setosa species is defined first in the file, and the Virginica species is defined at the bottom of the file. And each of these items has a different number to it. So there are a total of 150 data points in this file. All good so far. So these are the data that we will be visualizing again and again. Now I'm going to start in each case with what we call a base plot. I'm using the base functions of R, the stuff that ships with it, to do the visualization, and then we'll try to see if we can make our plots more informative or more beautiful by doing them in Ggplot instead. And in each case, you generally can improve the image quality that you get out of a base plot with some tinkering, but it tends to be in a somewhat inconsistent language. So Ggplot has tried to make plot construction just as straightforward as it can, as consistent in its language as possible. Okay, now that went very quickly. You saw that I entered the plot lines from this code, just using the plot command, which is basic to R. I entered that in R over here, and immediately this image showed up. So we've done a few things with this command. I'm going to walk through it in the browser window so we can see what it has done. Everyone got a plot looking like that? Great. Okay. So let's talk about why you were able to produce the image that you saw there. With plot, in this case, we are providing it X and Y information. And when you provide X and Y information to the plot function, and those vectors have the same lengths, it's going to interpret that as the command to create a scatter plot, a bunch of points out in this XY axis in Cartesian coordinates. So we see that X is referring itself to iris $ sepal length. Does everyone remember what $ is good for? Iris in this case is a data frame, and sepal.length is one of the fields, one of the columns of iris. So the software doesn't want all of iris, it just wants sepal.length as the X values. So by saying iris $sepal length, it's saying from iris choose this column. Likewise with Y, we're specifying that we want to subset out just the sepal width column, nothing else. The rest of this might be just completely obvious, but I'll just state it outright because it's worthwhile. We're specifying that there will be an X label for the X-axis, and that's just given as equals sepal length. And we're going to specify another axis label for Y called sepal width. And as usual in a base plot statement, we can say main equals sepal length and width. So how did that manifest itself? Well, we see that sepal length and width indeed showed up at the top. We didn't specify a font size or a font face for it, so it just used defaults. We've got our X label here and our Y label here already rotated for us. Did we at some point specify what Y range should be shown? Let's look back at this. Did we include that anywhere here? We did not. Okay, as a result, R took a look at what the range of values were that appeared in iris sepal length and the range of values that appeared in iris sepal width, and from each of those inferred what would be an appropriate range, what would lead to all of those data points being on there. Now, would it be possible to make this same plot in a way that does not use automatic limits? Yes, it would. So I believe I've already used, if we do that here, I'm going to try to enter this first line of plot. Here's the second line of the plot. And now I'm going to add in another one called xlim. Xlim equals 4.0, comma 10.0. And then I need an end parenthesis if I remember correctly. Yeah, I think that's right. Okay. So adding in an xlim element has now forced the x-axis of this graph to shift to 4 through 10. So we have lots of options when we make a scatter plot like this, and base graphics will let you tinker with things just as the Ggplot does, but less consistently. We had a question over here. Oh, sure. Sorry. Let me show broadly what that looked like. So what I did was to change the original call to plot to add one more argument over here at the extreme right. It wasn't very neat, I'm afraid. But you can see that I added xlim equals c 4 through 10. What you should remember from the previous days of this week is that when you use c, it creates a series of numbers. The first one was 4, the second one is 10. And xlim interprets those as the range of values showable on the x-axis. Thank you for pausing me there. Yeah, I wanted to make sure you could see that rather than just my typing in a little corner there. Okay, so the impact was felt by changing the x-axis in response. There are no data points over there. You can see that we, by adding 2 extra units to the x-axis, we just created a bunch of white space and there's nothing in there. So the software is using the full range of the data to set those limits by default. Okay, so we can do some customization of these plots in base graphics. I see some head shakes. Didn't work? Okay. You added the xlim statement. I'll take a quick look. That one didn't work. Now it works. Okay, good. Anything else? This one's not working. All right, let's make sure that the base scatter plot works. Go over to R, you plot that, and you hit enter. Oh, is he? Oh, yes. Okay. Comma, xlim, blah blah blah. Yeah. Good. Yeah. Sure, I'll show the code. Yes. Okay. The code that I'm using is exactly the same as it appears in the file, with the exception that I've added xlim onto that second line after main blah blah blah. So don't forget, you have to have a parenthesis to end the whole call to plot at the end of that as well. So parenthesis. Still no joy over there. Let's take a quick look. It should be apparent by now that if you have an awful lot of complexity to your call to plot, you kind of have to keep track of how many times you open parentheses and make sure you close them all off at the end. Otherwise, you end up with not much. So move it. So you need to come inside that parenthesis, comma, xlim, and then all the stuff for it, and then you can add a parenthesis at the end of that. Okay. So parentheses have bitten us again. All right. Any questions we need to address about that? Yes. Are you entering a full run? You have to have the line that starts with one as well. Let me grab the original text. Okay, so we're going to repeat the first command, and then we're going to repeat the next line. But this one we're going to hold. Yeah, I'm sorry, yes. Oh, okay, we have one more question at the back. Yes. Okay, there was a lot of conversation there, so I need to make sure I've addressed everybody kind of questions. So if you're talking, I'm concerned. Oh, I need to go fix something over there. Is everyone square on this? I know that there There were a couple different challenges that showed up as people tried to repeat the example of what I did here. One of the most common ones was that people did not remember to paste in the first part of the plot statement in order to change that second line. The second line can't operate without the first line being in front of it. Remember, the first line opens parentheses for the plot command, and that extends all the way through to the second line. So you can't just run the second line in isolation like that. Okay, so there are some complexities to when you have a very complex function call that spans over multiple lines. You're definitely running into that. The other piece was that somebody was copying from the terminal itself, and they grabbed everything from the plus at the start of the line through the end of the line. That plus was put there by the user interface to tell you this line is continuing from the one above that. So that's problematic as well. You'll note that in the text that we have on our browser window, there is no plus at the start of the second line. But if you try to copy it out of the window of running R, it's going to have put a plus there for you. I'll show you where that plus shows up here. So if I just repeat the original two lines, you see this little plus right here? If you try to copy text out of the terminal and paste it back in, it's going to add that plus in there and ruin your whole day. So yeah, it's a little tricky that you can't just directly copy stuff from the interface and run it again in that respect. Okay, so let us move now to the Ggplot version, and you can decide if you like it better or worse. Most people who care about data science have really adopted this grammar of graphics approach. One of the big things that you can accomplish with grammar of graphics is build a plot one element at a time. So let's do this. We see that we're going to start with the line scatter equals ggplot blah 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 blah. So I'm going to just run this line by itself. You should see nothing happens. So that's a little disturbing for some people, but this is just my old plot. I'm going to go ahead and pull this off screen now. So we see that running scatter by itself, setting the variable scatter to be equal to that line, does not produce a visualization in itself. You can see what scatter itself looks like by just typing scatter by itself now. Now it exists. But you see it's just blank. Scatter by itself did not create a plot because the plot does not include a geometry. And a geometry, a geom, in the world of Ggplot 2, is necessary for explaining how those data points translate into an image on screen. We did, however, set up an aesthetic. An aesthetic, that is one of the other key things here. So we've told it the data to be plotted are going to come from Iris, and the aesthetic that will govern how this plot should work is that we will be representing as an x-coordinate the sepal length, which is the same as what we did up above. The y-coordinate, where its position on the y-axis, will be handling the sepal width, and the color is going to reflect the species. So far so good. Aesthetic in your mind should already be saying to you that, okay, an aesthetic is where something is positioned, or it reflects the color that it takes on. And one of the other possibilities is that the shape it takes on is also governed by aesthetic. So now let us go ahead to grab the next line, and here we're finally going to add a geometry on top of that scatter object that was created. Okay, I need to close this little guy out of the way. Boop. All right, and now I'm going to paste in the second line. There we go. I'm going to tile these vertically so we can see one beside the other. Actually, I might try the other way. Horizontal might be okay. I'll try that. That way you can see the full line that we're typing. All right, so several things have happened now. We still have our plot, but remember that we've done something that wasn't in our base graphics command. Instead of plotting each species separately in the scatter plot that we originally created, we just plotted it as is. So every plant got a circle regardless of which species it came from. But in this case, we were able to tell Ggplot in its graph setup that the color was going to be set based on species. Species is what we call a discrete variable, or what we've seen in other cases, a factor. There are 3 different values that appear in the species field, and it's going to use a different color for each of those values. All right, so we see that already we have our pretty image, and we also note that we're getting some of the takeaways that usually show up under default formatting with Ggplot. We've got a gray area to show the plot point. We have a legend over here to reflect the colors that were set for that were used to represent each species, and we have our column, our X and Y labels. Now, I pulled out the stuff that was going to set a label for the main plot, but we can add that much as it is in the ordinary plot command. If you go to the URL that's given at the top of these directions, you can see how to add something like a main text over these plots. I've tried to keep these just as minimal as I could in this case. Okay, so what we've done is to build a figure by creating an object here called scatter that's storing all the information of the plot, that stores an aesthetic, where the points are, what color they are, what shape they are, and we have added a geometry, in this case a scatterplot, which is called a geom point in the Ggplot world, in order to represent it. But did we change the value of scatter when we added geom point like that? Let's try that again. We'll come in here and type scatter by itself and see what happens. Bunch of nothing, right? No data points represented. If I do scatter plus geom point, it populates it. But scatter itself was not changed when we ran that line saying scatter plus geom point. This is what I mean by saying Ggplot builds these images layer by layer. In this case, we have the object scatter that represents the data of the graph. We then add a geom that causes it to show the actual points. That's going to become a little clearer as we move further on, but for now I just want you to keep that in mind. The object representing the data is not the same object as what we see on screen, because here we're adding geom point as a graphical element on top of it. All right, so we had our scatter graphic. Oh, good, I did have one other thing. I snuck it in here. You could put this all on one line if you really wanted to. But so scatter, our base graph object, can have a scatter plot added on top of it. And in this case, we're going to add a linear model on top of that. Aha! So let me pull that larger here. So we've already done a bit of math here, haven't we? Can anyone tell me what a linear model is useful for in this case? A linear model. First off, are those lines straight or curved? We've got two impressions on this one. All right. So I'm going to note that the lines themselves, the red, the green, and the blue, are all perfectly straight lines. But the area around them is curved. That's because the lines represent a linear fit. When we created this object, we told it that our x values are going to be what? Sepal length, right? The y values are going to be what? Sepal width. Whether it's the scatter plot or the linear model object, they're both going to use these same x and y values. So when we added a linear model fit to this, a geom to this as another layer on top of this graph, it said, okay, you must be trying to predict the value of y based on x, because that's kind of how much of this linear modeling stuff goes. So by telling it to create a linear model, the software has sought what line best allows us to predict the value of sepal width on the basis of sepal length. Conceptually, this is not that weird an idea. A plant that has really long sepals probably also has pretty wide sepals. And a plant that has really small, very, very short sepals is likely to have very narrow sepals. So this correspondence in size is something that you would expect. The linear model here is showing in the line its mathematical model, and those curved boundaries around it are saying how confident is it at this point in the modeling. As you would expect, the values at the very extremes, the very smallest sepals for Setosa, for example, and the very largest sepals for Setosa, have the least confidence about their about how wide they should be in response to width, in response to length rather. So this linear model is doing some math for us, just making it part of the visualization. And in this case, the only thing we had to add was the geom smooth method linear model. The software already knew to separate the three species because we had told it to separate the three species on the basis of color. So it's a pretty smart graphing library to be able to take so much of this into account. If you were trying to add a linear model in base graphics, you would have to fit those linear models separately and then come back in and plot them on top of the scatter plot, which is kind of a pain. So having it all built in like this is quite nice. Okay, now this is not going to be a lecture about dynamite plots. Has anyone heard the term dynamite plot before? Dynamite plots, I'm afraid, are a graduate student special. They're a graduate student special at Vanderbilt University, they're a graduate student special at Stellenbosch University, and they're a graduate student special here at University of the Western Cape. I hate dynamite plots with a bitter and abiding passion. So what is a dynamite plot so that you can avoid seeing me scrunch up my face when I attend your eventual graduation? It's a bar plot with one whisker on each bar. We've all seen them. You can hardly go to a poster session without seeing them. Bar plot, bar, 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 each one with one whisker pointing up. When you ask students and professors about their dynamite plots, they often get quite defensive. If you ask them, what does that whisker represent? You'll frequently hear them say something like, well, that's the standard error of each bar. And then you can ask, why did you choose to represent standard error by that whisker on each bar? And they say something to the effect of, well, it was the smallest, because they want their data to look consistent. This is not a good answer. Okay, so dynamite plots, bad. Dynamite plots get my blood pressure up, so let's not do them. Instead, when you have multiple data points, say 5 replicates, instead of representing them as a bar plus a whisker, why not represent them as a box plot, which helps us to know about the distribution of those values. Now, box plots are built into R, as you can see. We're again just going to use the values from iris. We're going to be showing species separation on the x-axis and sepal length on the y-axis. So I'm going to just copy this as is for now. Okay, close this out. Close device. Click, click, click. There we go. There we go. This is a base box plot. Now there's something, I'm going to actually switch that back to horizontal tile. Okay. Oh, sorry, that really scrunches it, but we'll just deal with it. I want to explain that R has a standard language for representing the relationships of variables. And you can see that this one right here is the equation. So this is, it might seem kind of weird. Does anyone know what that little symbol is called between them? This little squiggle right here. Approximation is typically a pair of those, but in this case it's a tilde. A tilde is the name of that accent. When you see the word, when you see the phrase El Nino, for example, the tilde over the N tells you that it should be a ñ sound rather than a n sound. I was astonished the first time I heard someone say El Nino. It was a shocking thing. That's okay. So here we see sepal length tilde species. So how are we to understand that? I would hope that you'd understand it something like a statistician saying sepal length is a function of species. Do you see that? So species is determinant. It has some sort of determinant power in affecting sepal length. So when we specify this relationship as the first line of our boxplot call, the software is going to say, I need to separate the data on this field, on species. So remember that our original table had 150 plants measured, 50 from each of these three species. Boxplot has now separated them out on that basis, and each one of them gets its very own box. So how do we interpret a boxplot? Folks have seen these before? Okay. The most common way that we evaluate these plots is to say these are quartiles. It kind of depends which rules get used, but this bar down the middle of the box typically represents the median. Now, I asked you the other day, what is a median value? And I like the answer. It's the middle value. So you sort all the values from smallest to biggest, and you find the one that's in the middle of the list, and you report that as the median value for that set. So here it is. The median value is shown by this middle bar. We also have a 75th percentile value, or the third quartile, and the 25th percentile, or the first quartile. So these tell us where are the middle 50% of all of these data distributed. They're all inside that box. But typically, we have data that stretch outside that, of course. So the middle 50% are inside the box. This usually represents the maximum for your distribution, and this usually represents the minimum for your distribution. In some cases, you have data that fall far outside the ambit of the rest of the numbers. And you can see that in Virginica, we have an example of that. We have an abnormally low value for one of the plants in Virginica. As a result, it's been shown as an outlier, as a separate dot marked separately from the others. So this is not a minimum value for Virginica at this lower whisker. This is the lowest value for Virginica, but it's outside the box and whisker because it's so different. What rules people use for saying this is an outlier or not an outlier can differ from plot to plot, so it's worth knowing which one is in use. I think this one defaults to Tukey's method, T-U-K-E-Y. He was a very famous mathematician. Okay, so the box plot was pretty easy to get at. Now, for people who are clinging to Excel with your bitter fingertips, how easy is it to get a box plot out of Microsoft Excel? Have you done one? At the start of last year, I shot a little video for another statistical tutorial in which I recreated the process of making a box plot in Excel. And I have to say, it is a pain. It is a royal pain. So here you can see it was relatively painless. So it might actually be to your benefit to make use of tools like R for this purpose. All right, so that again is the base graphics function for creating a box plot. It is originally called boxplot. Very good. Let us now come back to our script. This time, we're going to create a box object that represents the data stored in a ggplot, given to a ggplot function. Again, we have aesthetics. Are they the same aesthetics as what we used above? I'm going to scoot up a little. They are not the same. So before we said X is going to be sepal length and Y is sepal width and color is species. Not this time. Now we're going to say X is species, so we're going to do our separation on the same basis in both the base call and in our ggplot call, and Y is just going to be species length. So that is the same, sepal length rather, which is the same as it was up above. So I'm going to run both commands together, but I want you to keep in mind that box is killing me here. Let me grab this. All right, I'll just grab all three lines. There we go. So box is receiving the object that represents the plot. To render the plot as a box plot, we're going to add a layer, a geom layer, in which we fill our boxes to reflect the species that this one is. Okay, so let's go ahead and just run that. Boom. There it is. So not very different, is it? Looks quite a lot like the one we just saw. Instead of showing the whiskers with little T handles on them, it just shows them as stretching out lines. That's not so different. Do both systems recognize the same outliers? They do. Yes, in both cases, Virginica's smallest value is shown as an outlier. So that's all quite lovely. And again, we have this nice color legend on the side. Did we get a legend before? We did. Okay, good. But did it do it in color? No. Okay, so color is just one of these things that comes along with doing things in Ggplot. Okay, now this time we're going to redo our function call. We still have the box object. We're still going to layer on a geom of a box plot, but this time we're going to add a statistical summary on top of that. So in both cases, we've started with an object, added the first layer that presents kind of the plottiness of it, and then we add another element as an analysis of those data. So if I come over here, all right, I'm going to click over here. So not much changed, did it? Okay, what were we asking for in our stat summary? The function on the y-axis is to look for a mean. The geom that will represent the conclusion of this mean function will be a point. It will be a size that's size 4. I mean, you could make it huge with like size 14 or something. And shape is set to 5. Now, shape could be something else, right? We could change that value. Let me glom all this together here. So what are some of the other options that we had for shape? Let me tile horizontally. All right, and now I'm going to type it. Oops, it's not that. Oh, goodness me. Okay, that's the original. I'm going to redo that first part back up to this one, and this time I'm going to change the shape to number 4. Okay, so we went from diamonds to X's by changing that. I can change it again. What's shape 3? Shape 3 is little pluses. So you see you have some customizability here. You could even make them ridiculous sizes. So let's change that to size 14. Oh, it doesn't like that one very much. All right, how about size 10? Can we settle for that? Doesn't like that one either. 8? Nope. Oh, sorry, I'm messing things up here. I'm forgetting to include the first line. Okay, size 8. There we go. That's a size 8 diamond. Okay, so you have some ability to choose which metrics would be useful, which statistics would be useful to you in representing it. Let me see. I'm going to open that up full screen for just a moment. In which cases do we see that the median is furthest from the mean? Is this one, that seems pretty similar? I think that one's pretty similar. The diamond is positioned just right in the middle there. But this guy is up a little bit, and this one is up even more. Okay, so if you use median rather than mean to characterize a distribution, are those values always going to be the same? They're not. Typically, they'll be very, very similar, but in cases where you have a distribution that's not normal, that's not bell-shaped like we've talked about, you're going to see some distance between where the mean sits and where the median sits. Okay, so by doing this statistic, we were able to show both on one plot. Where is this going to come into play? It's going to come into play because you're going to walk into your advisor's office and say, here, I've got a plot that I want to include on my poster. And your advisor will say, well, that's a box plot. Where's the average value for all that? Well, now you know how to add it on, right? Ggplot makes that a one-liner to add. So it's helpful to be able to revise your image in this way. All right. I have one more thing I want to show here. Frequently, we have a small enough number of data points that we can show them all. I mean, a box plot is a representation of the data. It shows the interquartile, the median, the bounds, the range typically. But wouldn't it be nice if we could just show all of the data points underlying that figure? In this case, if we replace that statistics summary with a geom jitter, we're going to see a jitter plot where the data points are superimposed on the box underneath it. Okay, so I'm going to run that. Look at that. So you have the option to show all of your data points. How many of you will end up doing an experiment where you have 100 replicates in each cohort for your paper? With biotechnology, frequently you have a relatively small number of data points. I want to point out that one of your alternatives to doing a box plot, to doing a dynamite plot, is to show all of the data points. If you've got 3 or 5 or 7 replicates, it's certainly not going to kill you to just show all 7 of the points. And here, it's just a one-liner. We added geom jitter, added on top of what we already had, and boom, now we have all the data points there. There are some people who say, well, that's too busy, I can't deal with that. And certainly if you have 200 values for each of these plants, it would be kind of a frustrating mess to try to read. But a jitter plot can make it possible to scale up to 50 data points without much of a problem. As you can see, there are 50 points in each of these three sets. So by doing this in Ggplot, we're able to add to the construction of this image layer by layer and decide which things we want to keep and which things we want to toss without a huge amount of coding effort behind that. Everyone good with that? Great. Okay, now we have talked a little bit about histograms, and we saw that it was really easy to get histograms because we could just use hist. Always sounds like you're about to whisper something to somebody when you say that. Hist! You'd see that in maybe a Robert Louis Stevenson novel. Okay. So now we could make this call very, very simply. We could just say hist iris sepal width, right? That's the small version of this. That by itself will already give you a histogram, so nice and easy. The call we've chosen is a little different, though, because it gives us an X label. Sepal width is a little friendlier way to say it. Our Y label is called frequency, and our main title is histogram of iris sepal width. Oh, it's supposed to be histogram of sepal width, sorry. There we go, I had forgotten to replace that. Okay, so histograms are easy to do in R by default, but that is also feasible here. So we will create a histogram object with the Ggplot call, and then we'll add on top of that the geometry of the histogram. Okay, now you'll note that we passed an argument to geom histogram. What does it mean? What is a bin width all about? Does anyone know? Okay, a histogram is about how popular is each size. So the data for sepal width in this case is a continuous distribution. You could have values that are just anything but on this 2 to 4 range. It could be 3.66253, whatever. So there's no inherent way to split up that space. If you were to say histogram without bin width in place, the software actually gets kind of fussy. It says, well, I assume that a histogram of about 30 bars is good, and so it tries to produce that plot, but it looks kind of terrible, doesn't it? But if you were to specify, I want my bin widths to be 0.2 wide, so everything from, let's say, 2 to 2.2 is one bin. Everything from 2.2 to 2.4 is a bin. Your plot comes out a little nicer. So you have the ability to do customization as part of these calls to these different layers of the graph. Okay. I was happy to discover, though, that if you mess with this a little bit, on top of adding bin width, if you specify that the border color for the boxes to be black and that the aesthetic is that the fill color for each bar is species, you can get a nice little visual separation of these colors. You can see here that the graph hasn't changed shape at all. I'm going to repeat that plot. See how that shape is identical to this shape? In both cases, it's just counting how many things fell in each case. But now it's sorting within each bar to say how many of these came from setosa, how many of them came from versicolor, and how many of them came from virginica. So again, Ggplot is going to offer us just a little bit more functionality as we move along and make it a little easier for us to understand which species are adding to which bin. Very powerful, I think. Any questions so far? Yes, please.
I didn't really understand what you meant by that.
Oh, okay. When we produced our original histogram, we had simple counts. How many of the 150 plants fell into which of these bin sizes for sepal width? Okay? So this is just telling us which plants, what number of plants showed up in each. When we ran the second line, however, we specified that we wanted the species to be represented by a color within these bars. So in effect, we're changing each bar of the histogram from one gray shape that's tall or small into a stack of 3 bars, each one reflecting the color of that corresponding species.
No, I get that.
Oh, sorry.
The one before that, the spaces. When you show the graph, the spaces are pretty.
Oh, okay, yeah. Okay. So the very, very simple thing. If I do just histogram plus geom histogram, right? Okay, so the software has already given us a warning. You see that it was trying to do its binning, and it assumed that having 30 bins would be a good choice, but ultimately it didn't think it was very nice. The software evaluated what the result would look like and said, well, I'm not very satisfied with that. So if bins is 30, how many plants did we have to begin with for this whole table? 150. There were 50 in each of 3 species. So it's trying to fit 150 counts into this space. And what it finds is that it's got these awkward gaps in here. And so the software is notifying us, I don't think I did a good job. So if we provide it a little hint to say we don't actually want 30 bins, you could do it differently. You could say, instead of providing a bins width, I think you can do something like bins equals 10. So, I mean, you can do that. You can tell it the number of bins you want. Or you can say, I think that the property on which we're separating could fall into 0.2 widths, and that would be okay. It's not that different than bins equals 10. It's a little higher. I don't know, is it 14? It's not that either. But here you can either tell it, I want you to categorize these in fifths of a millimeter, or I want it to, or you can specify how many total bins there should be. They're really interchangeable approaches. But when you tell the software, use your own judgment, it's dissatisfied with the result. That's why it gave us the warning message. Okay, I'm sorry, I should have explained that better. Okay, are there other questions? Okay, so let's come back in here. Coming up on, okay, so I've given myself 6 minutes, and so I've put in the grand finale section here. Having a pretty graphic to show yourself on your R screen is really nice. Let me come back to the pretty one here. So I like this image, right? And because I'm using R, I think to myself, well, I need to get this out somehow. So I can come up here to the File menu and say Save As one of these options. I could do that. And that will work. However, it's frequently the case that you're running through a long script of things and you want to have a whole set of images output to a file. So for something like that, it's really valuable that we have a set of export options built in here. So we have a function called PDF, which basically says whatever you're about to show next, I want you to write it to a PDF file rather than showing it on screen. There are several options here. You could use something called the dev EMF option, which creates this scalable graphic you can put into PowerPoint or Word very easily. You can also output things like PNGs or GIFs or JPEGs directly from the software. So I'm just including PDF as a little marker here to say you can export directly to PDF. So in this case, we're going to grab all of the images, the final images that we had in each of these 3 cases, and we're going to write them to a single PDF. So I copy this, come over here and paste it in, and we see no image was created here. Did you see that? It doesn't create a graph on screen. But it does respond with null device, which is to say that right now there is no graphics object open. So in having done that, we can look in this directory and see that it has now output a file called output.pdf. I seem to recall that I threw that in my documents directory, which is just crowded with nonsense, but here we go, output. All right, so when we open that up in Acrobat, we see that it has, in fact, okay, I really, really hate this new user interface. They really need to get rid of that. I'll just do it. I will fit one full page. So we see that this is a 3-page PDF. Each of these figures has here been exported as an individual page. So first page is sepal width versus sepal length. That's the linear model fit on a scatter plot. Page 2 is our jitter plot. Page 3 is our bar graph. So now when my advisor says, gosh, what have you done for me lately? Sorry, I'm mimicking bad advisors over time. I could just send my advisor this PDF saying, here's what I've been thinking about. I think you'll find page 3 very interesting. There you go. So PDF output is trivial here. You don't have to have a PDF printer installed. You don't have to have any special software. If you want to write a JPEG instead, you can do that, and it'll output a JPEG graphic instead, or a PNG. I would strongly urge people who are writing figures not to use JPEG. I know that we're accustomed to using JPEG with Instagram. I know we're using JPEG all the time with cameras. It's great for photographic images. JPEG is terrible for scientific line art, so don't do it. There really are many better options to work with. In this case, I would just point out that you have the ability to zoom basically infinitely on this. So by creating a PDF, we have this very sharp image all the way down to the smallest of scales. This is something that we call vector graphics format. If I move down here, look how sharp that is. I mean, we're looking at this at 800%, and the characters are just sharp as they could be. That is because PDF is storing each stroke, each font, every character. It's not storing a bitmap, which is just a grid of dots, which is what you get with something like a PNG or a JPEG. So if you need to represent your graphics in a way that's usable later on a poster, this is a pretty great option. If you are only going to use this graphic as kind of a throwaway thing, sure, make a JPEG. Knock yourself out. But by the time you want to publish your research, you really want crystal clear figures. And one way to do that is to use vector formats like SVG, PDF, or EMF, rather than things like JPEG and bitmap. Sorry, that's probably a point for another day. But it's worth thinking about. R has the ability to output the images directly to files. Here we use the example of PDF, but there are lots of other options too. Okay, with that, I am pleased to say we're done with day 4 tutorial. Tomorrow, we will be looking at t-testing, a whole lot of t-testing, and we're going to evaluate how many times we have to do experiments in order to find a difference when one exists but is very small and stuff like that. Tomorrow morning at 9 o'clock, we will be discussing biological pathways and networks. So I hope you'll be back here tomorrow morning at 9 for that. Thank you very much.